All right, for bell work today, we got a review of yesterday. Tell me what is the third term of the binomial expansion a minus 6b to the fifth power. 3 minutes. And then we'll go over. Yeah. We'll have a where all the T-West people will. See people like works. Right. Yeah, except will be in the other. I don't know, maybe I'll put the staff up. You're probably not staff up. I do that expect. Maybe some services will I've had most members would just be like, these are the wear a mask. I could explain something. Yeah. Correct. This is an example we want to use 5 twos. That second number tells you the power of the second term. Second part, we'll call it second component. And keep in mind that the first term, a to the 0, b, a to the 5, b to the 0. So it starts counting at 0. So that the second term would have a power of 1. The third term would have a power of. Yes, that's why. Yep, 0, 1, 2, 3, 4, 5. It starts counting 0 for the powers and for the rows of the Pascal sign. You would use 5. Yeah. The first term is the 0 powers. No problem. It's the hardest thing about this lesson is when to start counting at 0 and when not to. This is such a minor detail. All right, let's go over it. So the first term of this expansion would be a to the 5th negative 6b to the 0 power with a coefficient of 5c0. That's the first term in the sequence. Right, you start the a power at the maximum, 5. You start the second component's power at 0. The next term would be then 5, choose 1, a to the 4th, negative 6b to the 1st. That would be the second term. So for us, if we want the third term, that would be 5, choose 2, a to the 3rd, negative 6b to the 2nd. And then you have to tell me what that is. If you have 5 birthday presents, 5 presents, and you can choose 2 of them to have for your birthday. This is probably the weirdest analogy. There's probably a much better analogy. You have 5 different kinds of pizza And you could choose a slice from each pizza, 2 slices. How many different ways could you do it? It'd be 1, 2, 3, 4, 5, 6, 7, 8. Oh gosh, 9, 10. Is it 10? It's 10. Or just type it into a calculator. A cubed negative 6 squared is 36 b squared, or 360 a cubed b squared. Why didn't I just do that as my analogy? How many different ways can you hold up 2 fingers out of 5? Stupid, Mr. Lake, just dumb. All right, everyone happy? Great. Let's do oh, today is a fun day. Today, I get to teach you how to count. Isn't that great? Like you started out grade school, like, hey, let's talk about how to count, by 1s and 2s and all that kind of stuff. Now I get to teach you how to count again. All right, we will do simple counting problems using the fundamental counting principle to do slightly more complicated ones. And then we will learn how to use permutations and combinations to do slightly more complicated ones. All right. So you might say, Mr. Lake, I already know how to count. Well, let's see. Let's say you have 8 pieces of paper. You label each piece of paper from 1 to 8. You put them all in a box. You draw 1 out of the box, record its number, put it back in the box, draw another piece of paper randomly out of the box, record its number. How many different ways can you get a sum of 12? I'll give you one. One way that could happen is if you draw a 4 as your first number and an 8 as the second number. That's one way you could get a sum of 12. Can you tell me another way you could get a sum of 12? 3 minutes to see all the different ways that you can draw those 2 pieces of paper such that you get a sum of 12. If you want to go into law school, these are the type of problems on the law school admissions test. Kind of. There's a little bit more to it. All right, what's another way I could draw to get the sum of 12? If I draw a 6 and a 6, that would give me another. What's another way I could do it? Seven and 5. And also 5 and 7, right? Is there any others? I think there's one more. 8 and 4, right? 8 of the first one, 4 of the second. So I believe that gives us a total of 5. Yay? Hey, we just did our first counting problem. Look at you. Counting to 5. Hot dog. All right. Anybody? Yeah. This one you do replace the paper back of the box. No, I think you're going to do the second. I think you're looking at the next one. The next one is don't put the paper back in the box, right? Yeah. Which actually, if you got these. All right, next one. Now you can't put the paper back in the box. Draw one at random. Draw the second at random. That's it. How many different ways could you obtain a sum of 12? I'm just going to do a minute for this one. So the only difference between this and the one we just did is now you don't put the paper back. Now it's just 4, right? Because we can't do 6, 6. If you do 6, 6, that gets canceled out because you can't put the 6 back in the box to draw it again. So now it's only 4. How many total ways are there? Okay, in the first option, how many total different combinations are there that you could draw? There was 5 in the first one and 4 in this one. Under the first way, how many different ones are there that don't have a sum of 12? That's a good question, apparently. Yeah, that's a good question. You draw, there's 8 pieces of paper in a box. You draw one, record it, put it back, draw another one, record it, put it back. How many different ways could that happen? It's 8 by, what did you say? 8 by 8. Right, because you got 8 choices for the first option, put it back, and you have 8 choices for the second option. So you have a 64. So then the chances of getting a sum of 12 out of that is about 7.8%. In this game, do you think it's better or worse? Are you more likely or less likely to get a sum of 12 in the second game? In the second game, how many different total possible combinations are there? You draw, you have 8 paper, you draw one out, you don't put it back, you draw another out. How many total possibilities are there? Well, there was 4 to get a sum of 12. Now we don't care about that. Just how many different? You could draw 1 and an 8. That's one way it could happen. You could draw a 1 and a 7, a 1 and a 6, a 1 and a 5. How many total different ways is there? Yes, it is 56. How'd you get that? 8 times 7. On the first one, you have 8 pieces of paper to choose from, right? And the second, you have 7 because one's been removed. So that's 4 out of 56. What's that? Oh, it's actually pretty close. 7.14 to 1.4, if you will. So you're more likely to give a sum of 12 on the first one than you are on the second. Isn't that crazy? All right, well, we just did that math for finding the total number of different combinations is the fundamental counting principle. If you have 2 events, and the first event can occur in m different ways, and the second event can occur in some other number of different ways, then the number of ways that the 2 events can occur is the first total possibilities times the second number of possibilities. M1 times M2. So the first one, we had 8 choices. So that'd be 8 different ways that it could occur. And the second one, we had 7 choices. So you do 8 times 7. If you get to put the paper back, then it's 8 times 8 because you have 8 choices every time you draw. You understand how that principle works. You just count how many different ways it could happen for the first event, how many different ways can it happen for the second, and then you multiply. Anybody need more time to write? All right, so for example, how many 2 different letter words could there be in the English alphabet? They don't have to be actual real words that exist now, but how many could there be? I will give you one because I'm a generous spirit. The first word that could exist in the English alphabet that does it is AA. I've tried to get this one published as but they want the H at the end of it. They keep fighting me on that. One day, I'll get them to accept AA as a word. All right, that's one. There are a bunch more. Find all of them. Not really find all of them. Tell me how many there are. There are 26 letters in the English alphabet, if that helps. Right? Anyone want to find me on that? It's 26, right? It's 26. It is 26 letters. Pretty sure about that. 70% sure. Also, knowing all the 2-letter words that are vowels will improve your Scrabble game a whole lot. It's very important to know all the 2-letter words that are just vowels. It's how you win at Scrabble. IO, also the ones with Z and Q, ZA, ZA, that's a Scrabble word. Yes, it is. ZA. It's in the Scrabble official dictionary. ZA. You got to know those. And then I think QI. That's an important one to know. Right.
Scrabble, like dictionary to look at words.
No, I mean out loud. I just screamed Scrabble official dictionary. And then they got it. It's not perfect. It leaves a few words out, but it's pretty good. I'll walk around. If you're stuck on how many different possible 2-letter words could there be, let me know. I'll help you out. We get the answer. you have fun? Good. Are you more motivated to go to TCAP now? You lose like 4 classes. Or is it 3 or 4? It's 3. That's pretty tough. If you want to be a fan, it's pretty tough. Debate, forensics, acting, all these other electives. All right, how many different possible 2-letter words could exist in the English language? 676. How'd you get that? I have 26 choices for the first event. I have 26 choices for the second event. So that gives me 676. So now you have to think, if there's so many possible words that are just 2 letters, why do we have to have all these words that have like 1,000 letters in it? Couldn't we just take the word juxtaposition and just, now it's JU? Right? Or JX? If a math person invented language, it would be so much easier. Everything would be short. All right. Okay, that was your warm up. Now tell me, how many different phone numbers exist in the United States? There are a few restrictions. I take it back. Tell me how many phone numbers exist for each area code in the United States. So a phone number is the first 3 of your area code, like 785, and then followed by 7 digits. That's your local number. So here, let's just make it for the area code 785. How many different phone numbers exist in our area code? Note that at this time, your telephone number cannot begin with a 0 or 1. You cannot put a 0 or a 1 in this first spot. 3 minutes. Max? Did you have a question? Or are you ready? You already got the answer. Yeah. Yeah, you can't put a 0 or a 1 at the beginning. So for that one, you don't have 10 choices. You only have 8. The rest of them, you have 10 choices. I bet you there's other requirements too, other numbers you can't have. Like, I bet you they don't let you have the first 3 numbers as 911 either. Or 411. Or anything 11, to be honest. But we'll just deal with those 2 restrictions. First number can't be 0, first number can't be 1. Yeah. Times how many choices do you have for the second? And 10, right? Because it could be anything. It could be 0, 1, 9, 1, 2, 3, 4, 5, 6, 7, 8, or 9. The next number, you got 10 more choices. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You're going to tell me all the possible phone numbers we can have in our area code 785. Just in our area, not across the US. I got excited at the beginning. I had to tell the thing. Well, sure. That happens. All right. I think you're 1, 0. I just did that. 3. No, I think that's the Yeah. You get, take the time. More choices. There's 7 possibilities. You got, for the first one, you got 8 choices. Second, you got 10 choices. Third one, you got 10, 4, 5, 6, and 7. There. This one's, it's just the first number can't start with 0. How would that be? Yeah, that is set.
So there's only one choice for that, yes.
It does. Go back here. Did you got it? All right, let's go over it. Oh, I was supposed to call someone from seminar and I forgot. That's whoops. All right, for the area code, we only have one choice. I gave you that. That has to be 785. For this one, the first digit, how many choices do we have? 8. For the next digit, how many choices do we have? For the next one. And again, so we totally have 1, 2, 3, 4, 5, 6. 10 to the 6. If you take 1 times 8 times 10 to the 6, you get the answer 8 million. Which is not a problem for us. Our area code probably has plenty of numbers left, but you're in California, you could run out of phone numbers. And I have to break you up into different area codes. Yay? Look at this. Look at you all counting. Questions on this? You just go home to your mama or papa and you say, Mama, Papa, I can count now. All right, permutation. Now, permutations are a way of counting n elements so that we put those n elements in an arranged order. And I want to know how many different ways we can make that order. So one of the elements gets to be first in the order, another one gets to be second, another one gets to be third, and so on and so forth. Yay? Makes sense? A permutation is counting how many different ways could I order a set of stuff. So for example, how many different ways can I arrange the letters A, B, C, D, E, and F? I'm going to give you 2 this time. I'll give you 2 ways you could do it. The first way will shock you. That's one way to do it. Okay. You ready for another way I could do it? Boom. That's 2 ways I could do it. You know what I'm going to do? I'm going to give you a 3rd way. Look how generous old Mr. Lake is. Can you tell me the total different possible ways I could arrange those 6 letters? I haven't taught you how to do this yet. So this is a challenge question. If you can find the answer, I will be impressed. The answer is between 500 and 1,000. Good work. I think it's probably fun. I feel like all math classes should just be this. This is more important than geometry. And again, we're doing letters and numbers because that makes it easy, but this could be anything. This could be like you're doing, what do they call those? Bridal party? No. What's the ordering? How do you order the people that come up the rows? Whatever that is, right? Like the best man and the maid of honor go first, and then it's a pair, another pair, and another pair, right? Of people coming around. Is a bridal party? How many different ways could you order the bridal party to come down the aisle at your wedding? That's important information to know. Because you can't have Steve following Jacobs, because Jacobs is so much taller than Steve, that would look weird in the bridal party, right? So you have to have a buffer between Steve and Jacobs, right? And then Emily can't go down the aisle with Ben because that was a thing, right? This is important logical stuff. This is a first step to being able to do all this calculation. It's also literally on the LSAT. The LSAT will ask this question. This is a question on the LSAT. Except it will add like those little rules that I said. A can't be next to B. D has to be the last one in there. E can't be the first nor the last one. Which you already knew, right? It'll be something. So that's LSAT. All right, Friday's homework will be at law school admissions test. Those are fun. Those are fun questions right there. Okay. How many choices do I have for the first letter in the sequence? Six choices. How many choices do I have for the second letter in the sequence? Five, because I can't use the first letter, right? That's been removed. How many choices do I have for the third? Four, because now I can't use either of the first two. How many do I have for the fourth? Hey, where have you seen this before? That's a factorial. 6 times 5 times 4 times 3 times 2 times 1 is 720. Isn't that cool? Look at that. Factorials. So for any permutation of n elements, the number of possible different ways you could order those n elements is just n factorial. Isn't that great? Nice, easy. So, slightly different question. You have 8 horses that are running in a race: My Little Pony, Ponytail, Sir Lancelot, Harry Trotter, Post Stallone, Britney Spears, David Hasselhoffs, and Zebra. In how many different ways could these horses come in first, second, and third? I don't care what happens after that. Do I want to care about what happens after that? Okay, let's not care about what that. Yeah, let's not care about what that happens. I just want to know how many different ways can I get a first, second, and third horse. Also, as a requirement for answering this question correctly, you do have to pick your favorite horse. I have predetermined the winner, and if you pick the winner, you are a winner. Okay? There's a lot of good choices for winner. Okay? I know what you're thinking. Did Mr. Lake really spend time in preparing this lecture, looking up funny horse names? Is that what Mr. Lake did? On his plan period, his precious time, sat and Googled funny horse names and then typed that into a list. Yeah, I did that. I had to go to the second response in Google first because the first one was lame. Not funny. The second one had the puns. There was a lot of dad joke ones that I had to avoid too. The dad joke ones aren't funny in this instance, because it was stuff like, don't tell my wife was the name of the horse. And I'm like, pass on that joke. It's fine, it's fine. Okay, it's okay, but not my humor. Yeah. Harry Trotter is better than that. Right, Max? Yeah. Because it's like Harry Potter, right? But they replaced the Potter with Trotter because that's what horses do. And now it's funny. Right? Yeah. When you explain the joke, it improves it. All right, I'm gonna walk around. If you need help ordering 3 horses, let me know. Okay, you got it? That would be the total different possible way. I only need the first thing. So just use. I don't need all of that. That would be for all. So could I just be? Okay. Yeah. Yeah. Okay, so again, what we just learned is the total possible different ways this race could end is 8 factorial. I have 8 horses that need to be ordered from first to last. But all I care about is how many ways could it come in first, second, or third. So how many choices do I have for first place? How many choices did I have for second place? 8. So how many do I have for third place? Now we multiply those. And we get 336. Out of a total number, what is 8 factorial? It's probably really big. Out of the total, 40,320. All right. Who said that their favorite was Harry Trotter? Nobody? All right, that was the fact. That was third place. Zebra. That was second. The winner is, of course, Post Alone.
Yes, sir.
There you go. If you chose Post Alone, you are a winner today. Don't let anyone tell you else. Okay? All right. The next thing we're going to do is slightly more complicated. We are going to take a number of elements R at a time. To do that, you will do NPR. It's what we just did in the previous example. We had 8 total horses, but we were only taking 3 of them. We only cared about first, second, and third. So then we did 8 times 7 times 6. Another way you could have done that was to do 8P3. Yes, which would be 8 factorial over 8 minus 3 factorial, or in other words, 8 factorial over 5 factorial. Uh-oh. See if this is daycare. Nope. That might be the solar people, but I don't care about that. Okay, over 5 factorial, but that is just 8 times 7 times 6 times 5 factorial over 5 factorial, which cancels out and leaves you with just 8 times 7 times 6. So basically that math where we canceled out, we only cared about the first 3 and we didn't care what happened after that, is when you take a number of elements r at a time. In your calculator, you can do that. It is math. And then you go to the probability column, and it is option 2. NPR. It's also a radio station, NPR. It's pretty good. Yay? Okay. Anybody need more time to write any of that nonsense? If you do, just stop me. We're almost done with this lesson. We got plenty of time. Okay. All right. The last thing we have to talk about, another wrinkle that you can have in permutations besides the problem we just did, is what happens when you have duplicate elements. So not all the time will all of your elements be distinct, but sometimes in your set, you will have 2 elements that are the same, and you only want to count the distinguishable permutations. What you do then is you take your permutation and you divide it by permutations of your duplicates. Duplicates. If yours has so many of one kind and so many of a second and so many of a third, then you have to divide the total number of permutations by the possible combinations of your first, second, third, and so on and so forth. Really, it takes, let me show you an example of this. It'll make more sense after you see an example. And again, sometimes it won't matter if it's distinguishable. Sometimes it will matter if it's distinguishable. You really have to evaluate the context to see if you actually have to do this. I think on your homework, there's only one question that asks about it. All right, so for example, let's say you have the word banana and you want to rewrite banana using the same letters to make a new word. The issue is you have 3 A's, right? So if you tell me B, A, N, N, and then I swap these 2, I still get the same word, right? That's not a distinguishable order. So here's how you resolve that. I'm going to take my total number of letters, which how much is it? 1, 2, 3, 4, 5, 6 factorial. And I will divide it. I have 3 duplicate A's and 2 duplicate N's. And then that will give me only the choices where your A's are not swapping with each other and your N's are not swapping with each other. And then calculator. What is 6 factorial divided by 3 factorial times 2 factorial? Well, 6 factorial is 720 divided by 12 is 60. There are 60 different ways. Oh, I put an exclamation mark because I was excited, but we actually can't do that anymore. There are 60 different ways you can write a word using the word banana to make new words, like ban. That's the best choice. If you had to make a new word out of banana, ban is a good one. Yay? Does that make sense? Picking up what I'm putting down, buying what I'm selling. So whenever you have an order where you have duplicate elements and you want your final answers to be distinguishable, then you have to divide by your duplicates factorial. I feel like I'm going fast. Does that make sense? Do we need to take some time to ponder that philosophically? No? All right, all right. All right, your turn then. How many different words can you make off of the word mitosis? How many, I should say, how many distinguishable words can you make out of the word mitosis? 3 minutes. The answer is between 1 and 2,000. Yeah, that's right. How many different words can you make out of the word mitosis? Use this again. Read that again. Okay. Yeah. No. You multiply together. Oh, you, or basically, you only have to cancel one of them out. You're gonna cancel out both. Yeah, so if you divide that by 2, you get. So. But there are duplicate S's and duplicate I's. There's 2, so you have to divide by 2 again. One more time. Yeah. Yep. How many mitosis? How many? All right. How many total letters do we got? 7. So the total different ways I can order that is 7 factorial. And then I have to divide that because I have some duplicate letters. What do I have to divide that by? 2, because I have 2 I's, and well, 1, that's true. And another 2, because I have 2 S's as well. So then that is 5,040 divided by 2 times 2, which is 1,260 words. Yay? Okay with that? All right, last thing we're going to talk about today then is Well, what happens when the order doesn't matter? So far in all of our counting, the order has been important. But what if it doesn't matter? Well, in that case, you do not a permutation, but you do a combination. So you take n elements r at a time, and actually this is a formula you already have in your notes. It's the same formula we used to find the coefficients of the binomial theorem. N factorial divided by n minus r factorial times r factorial. Basically, it's the same as a permutation, but we include in the denominator r factorial to get rid of all of the, basically the duplicate answers, where the only thing that changed is the order. Again, we don't care if the only thing that changes is the order, because in a combination, order doesn't matter. For example, and how many different ways could you choose 3 letters A, B, C, D, and E? The choice A, B, C is one way you could do it. The choice C, A, B is a different order, but you still end up with the same 3 letters. So it doesn't matter, right? That's the same as this if we don't care about the order. So this is not a new way. Tell me how many different ways could I get 3 letters out of those 5? I should have changed this to pizza. I think I'm going to change this to pizza for my next year's class. Instead of letters, to pizza. It makes more sense. Pizza always helps. You know what? Why are we even delaying? Why are we delaying the inevitable? Let's fix it right now. Nope. Fix it. Okay. And how many different ways can 3 pizzas be chosen from 3 slices? That pizza be chosen from the selection of, all right, pepperoni, cheese. What's another one? Black olive. People like black olive. Yeah. What's another pizza? One topping. Sausage. Sure. People like that. And last choice. Hawaiian. What was the other choice? Fine. Hawaiian works. What's wrong with pepperoni? Did I spell pepperoni wrong? Is that possible? Oh, there's an E instead of an O? That was a test of you, Google. You passed. The order of the pizzas is not important. Okay, there we go. That's more relatable. Also, you can't pick from the same pie twice, okay? There are only 5 slices left, 1 from each pizza. What if you could pick from the same pie twice? Oh, yeah. All right, 3 minutes. You want 3 different slices of pizza because variety is the spice of life, right? The first answer is between 0 and 25. The second answer is between 1 and 10 million. All right. You gotta use this. Because the order doesn't matter. You gotta tell me how many possible elements are there, how many are you choosing from? Not quite. That's a permutation. This order could be cheese, pepperoni, black olive, or pepperoni, cheese, black olive. In which case you have a double count stuff. So you want to do this. 5, choose 3, 5 combinations. 5 C3. Probably. Option. There. Five, choose 3. Yep. That is right. The formula is that. That's what you're calculating there. Yeah, rather than typing it all out like it's a bracket and all that, you calculate it. We'll do it all. That's right. What about the it's between 1 and 10 million. Oh wait, did I lie? No, it's between 1 and 10 million. I just think. All right. Because the order doesn't matter, we want to do NCR instead of NPR. So you want to tell me what is, oh, here, before I start writing, stop share, reshare, whole screen. So we want to do, because order doesn't matter, 5 choices. I have 5 possible choices to pick from, and I am choosing 3 from those 5. So that is 5 C3, which is 10. And really, again, when it's 5 choices, choose 3. You could think of it like I have, how many different ways can you hold up 3 fingers? Right? 1, 2, 3, 4. No. Oh gosh. 5, 6, 7, 8, 9, 10. That was worth it. That demonstration was worth it. All of this math became clearer because I moved fingers up in the air. Right, Malachi? Malachi says, yeah. I'm the best teacher around. What are you gonna? These teaching techniques passed down through the ages. Okay, next one, the order also doesn't matter. Once you have your 5 cards that you're dealt in poker, you can rearrange your hand, right? It's your 5 cards. So I have a total number of 52 choices, and I will choose from 5 of those. So if we do 52 C5, math, C5 is 2,598,960. Out of those choices, how many is a royal flush? There are only 4 ways to get a royal flush, right? You have the ace, king, queen, jack, and 10, all of one suit. So you can have a royal flush in hearts, spades, clubs, and diamonds. So there are 4 possible ways to get a royal flush. Out of all of those options means that your chances of drawing a royal flush from a deck of cards is 0.0001%. Is that the right number of zeros? Let's write this out. That's 0.000001,539, or if you move the decimal place twice to make this a percentage, 0.0005 0.1539%. That's your chances of getting a royal flush out of it. Just not before you pass cards back and draw some more, but of getting it the first time your cards are dealt. Isn't that crazy? If you get a royal flush, it's like a once in a lifetime opportunity. Or what would that be? That'd be like 1 in 10,000. That'd be 1539 over 10, 100, 1,000, 10,000. No, more than that. I need 3 more zeros. Oh, no. Hold on. I want to do 1 in 10,000. Is that right? Yeah. 1 in 10,000 or 1.5 in 10,000 to be more exact. If you played poker 10,000 times, you would get a royal flush once, theoretically speaking. All right. That's a class. It is 12:17. You have the next 34, 33 minutes to work on the homework. Nobody should leave here with homework today because, oh shoot, there was another slide I was supposed to do. Did I put it in your guided notes, but not in this slide? That I did? No, I didn't. I just left that off. Hold on. I'll put one more thing up here before we go. Unless I just left it off completely. So you think you just walk in here?
Yeah.
You people.
How you doing?
Troublemakers.
Starting right now. You see it?
So you just walk in here after being, you missed. I taught these people how to count today.
You did?
Yeah. 1, then 2. After that comes 3.
These are essays.
Yeah.
Well, half of that is just in Spanish.
Yes, that's true.
It's a bilingual essay?
Yes.
Insane.
I was supposed to put these guidelines on there and I forgot. So here are your guidelines that will help you do the homework. When you are asking how to count something, you should ask yourself the following questions. First, does the order matter? If the answer is yes, a different order is a different result, then you need to do a permutation, NPR. Do they need to be distinguishable? Do you have duplicate elements and it matters if those are in a different order? Then you might have to divide by how many duplicate elements you have. If not, and the order doesn't matter, then you will do a combination. And then finally, is this just one event or is there multiple events? Like at the beginning of the class, we drew 2 times. In which case, then you have to calculate each event independently and then multiply your events together. Yay? That helped. These are good guidelines. I don't know why I didn't put them on the guide practice. Okay, you have the rest of the hour to work on the homework.